Okay.
Morning, everyone.
You too.
Morning, Dr. Praveen.
Can you switch off the other's mic?
Yes, 1 second. Srinivas ji,
You have I request you to give.
And this entry should be limited in the Teams. Where this YouTube, we can use it.
Mr. Srinivas, can you mute? Praveen ji, you can unmute now. Yeah. Rest everyone is muted.
Hello,
Yes, we
am
can
I
hear
audible?
you. Yes, yes.
Okay. So I welcome you all for this National Science Day celebration event, which is celebrated on 28th of February each year, for celebrating the discovery of Raman effect by Professor C.V. Raman, one of the Nobel laureates of the country. And this year, National Science Day theme has been Global Science for Global Well-being. And as we all know, Indian Society of Remote Sensing, which is one of the oldest scientific societies in India, has been celebrating the important scientific events, including National Science Day, for many years. And recently, we have also celebrated our Golden Jubilee event in IRS campus, Dehradun. So it gives me a great pleasure and welcoming you all for today's special popular lectures on the theme, which has been very carefully selected by our EC members and led by Dr. Poonam. Science and geospatial technology for archaeology. So, in the last few years, we have seen tremendous growth of this new technologies like terrestrial lidars, photogrammetric system, aerial platforms, aiding the discovery in the archaeology sector. And today we have very eminent panelist, Dr. V.N. Prabhakar, who is the Associate Professor of Humanities Social Science, well-known archaeologist from IIT Gandhinagar. Mrs. Shefali Agarwal, Madam, who is a Group Director of Geospatial Technology and Outreach Program Group at IRS Dehradun, and Madam's group has been leading the way in India to conduct many archaeological studies using terrestrial photogrammetric and lidar systems. Then we have Dr. M.B. Rajni, Associate Professor, School of Humanities, National Institute of Advanced Studies, Bangalore. And their team also is working in a recently launched big project in the archaeology. So I welcome you all for this National Science Day lecture. And I request Dr. Poonam to further continue the program.
Thank you, Dr. Praveen. So I welcome everyone in this National Science Day celebration. First of all, my greetings to everyone on National Science Day 2023. So in this particular session, we'll be having 3 sessions by our eminent personalities. So the first session would be by Dr. V.N. Prabhakar. So it is my privilege to appraise the audience about the brief resume of Dr. Prabhakar. So Dr. V.N. Prabhakar is currently Associate Professor Archaeology at Indian Institute of Technology, Gandhinagar. He has obtained his degree of Doctor in Philosophy in 2013 from Kurukshetra University on the topic Burial Practices of Hadappans with special reference to Sonoli excavation. He is working at IIT Gandhinagar since September 2020. Formerly, he has worked as Director, Exploration and Excavation at Indian Institute of Archaeology at Archaeological Survey of India between August 2018 to September 2020. Dr. Prabhakar has coordinated the exploration and excavation activities throughout the country and headed the Institute of Archaeology, which is an academic wing of ASI imparting education in archaeology, heritage management, and museology. He has expertise in Harappan civilization and has conducted excavations at Roopnagar in Punjab and Karanpura in Rajasthan, both belonging to Harappan culture, between 2011 to 14. From 2009 to 11, he was responsible for exploration and excavation, conservation and preservation of 166 nationally essential heritage structures, including the World Heritage Properties of Ajanta and Ellora caves. So Dr. Prabhakar will be talking today on the topic Science in Archaeology, case study from Harappan archaeology. So his presentation will give a brief introduction to Harappan culture and a few techniques that were used by different scholars and the author to interpret the Harappan culture. So thank you, Dr. Prabhakar, for accepting our invitation and giving your consent to deliver this talk. I now request to start Dr. Prabhakar's session. Please start Dr. Prabhakar's session.
Hello.
The society office. I request the society office.
I'm going to talk about sciences in archaeology and some of the few case studies that have been used in understanding various aspects of Harappan archaeology. First of all, I would like to acknowledge my guru, Professor R.S. Bisht, who is a guest professor here at IIT Gandhinagar and also a former Joint Director General ASI. And I'll also like to thank IIT Gandhinagar, Archaeological Survey of India, which is my parent organization. I also thank Indian Society of Remote Sensing Dehradun for giving me an opportunity to talk before you. And I also thank several archaeologists, and foremost are Professor Jonathan Markenoyer and Dr. Randall Law, who have collaborated with us in understanding various aspects of Harappan archaeology, particularly from the site of Dholavira. I also place on record the contribution of all scholars who have contributed in various manners in understanding the Harappan civilization. The story starts somewhere in 1924 on September 24, 1924. John Marshall, the then Archaeological Survey of India's Director General, he announced the discovery of the Harappan civilization based on the discoveries made from Harappa and Mohenjo-daro. So this was widely circulated, and immediately it was noticed by several scholars working in West Asia, where they noticed the Harappan artifacts in a datable context. Remember, at that particular point of time, the chronology of Mesopotamia was well understood, and hence the finding of Harappan artifacts from the datable context of a site in Iran. Here it is mentioned in the illustrated London News, dated September 27. There they mention about the findings by a particular archaeologist known as D. Morgan at Susa, where they date the Harappan artifacts to a 3rd millennium BCE context. So this is how the chronology of Harappan civilization, it was revealed as early as 1924 in the absence of radiocarbon dating techniques. The radiocarbon dating techniques, it emerged in the 1940s, which also paved the way for understanding the various chronological aspects related to this civilization, but that happened much later. So this relative chronology gave a firm footing, and through the course of nearly 100 years of its discovery, we have revealed, we have found out various aspects related to the Harappan civilization, thanks to the contribution of several archaeologists. A few of them have been listed here, and in particular, the site of Dholavira I would like to mention because it is one of the 5 largest Harappan settlements in the Indian subcontinent, and also some of the contributions to various understanding various aspects are from the sites of Harappa in Pakistan, Kalibanga in India, and also Mehergarh in Pakistan. So it's some of the few remarkable discoveries that help in understanding several facets of this Harappan civilization. And if we look into the number of sites, what we inherited in 1947 is that only Rangpur, that was the known Harappan site on the Indian side, and all the known sites it went to Pakistan. But a prolonged investigation by the Indian scholars, it led to discovery of many more sites. So nearly after 100 years of its discovery, we are now in a better situation to understand what is the contemporaneous civilizations like this Mesopotamia, Oman, and the Egyptian civilizations, and all the red color bars, they denote the urban phase of this civilization. So before the urban phase, we have a long antecedent phase where regional Chalcolithic cultures emerged. I mean, they were the initial towns and villages, and even before that, humans started to settle down around 7500 BCE, particularly in the Indian context, the South Asian context. We have the site of Mehergarh, where we have the earliest evidence of humans started to settling down, practicing agriculture, domesticating animals, and they were leading an agro-pastoral lifestyle. So slowly they were becoming sedentary. They were discarding the hunter-gatherer way of lifestyle. They were producing foods. They were having a lot of surplus food, and that gave an impetus to growth in population. So this growth in population also brought in several complexities in the social organization, and that's how we started to see various aspects related to social organization from Mehergarh itself. The settlement was large, divided into different parts within the overall occupation area. They were having long distance trade, and also a system of complex technology also starts to evolve. So all these kind of things, it gave a lot of growth to the settlement, and ultimately it grew from a village to a town to a larger town, and ultimately cities start to emerge. So that's how we see regional manifestations of various parts where the Harappan civilization now occupy. We have distinct regional cultures in Sindh, in Gujarat, in Makran, in Cholistan of Pakistan, in Punjab, where we have distinct regional cultures. So all these regional cultures were contemporary at one point of time, and they were also sharing some common ideology. And ultimately, at one point of time, they might have realized that we need to come together to harness the enormous raw material resources which are spread all around the greater Indus plains. It is not concentrated at one particular location, but it is located all around the Balochistan hills and the northern Pakistan hills, in the Himalayas, in the Aravallis, and in the Gujarat region. So if these resources have to be harnessed, they have to come together, and that's how the integration of these all regional cultures took place around 2600 BCE, that lasted for nearly 700 years. And towards the end of this long urban phase of the Harappan civilization, something happened on the climatic scale, and thanks to the recent researches on understanding the paleoclimate, Himalayan event, which is identified to the 4,200 years ago, something happened which triggered a series of climatic changes, change in the monsoon climatic regime, and it lasted maybe for nearly 100, 200 years, and that's how it triggered a transformation. It triggered the changes in the modes of economy, modes in the agricultural produce, and that could have led to the ultimate transformation of the urban civilization. It lost its urban character, and once again became a rural culture. Overall, the larger cities were abandoned. They migrated to areas where they could find more water. And coinciding with this is the drying up of the river Saraswati also. So this is a very long history which has been documented through various kind of analysis, various kind of multidisciplinary approaches, which is the present day requirement of understanding any former or ancient culture. So starting from Mehergarh, if we look into the earliest phases of occupation and at Mehergarh, we see the contribution of different sciences from here, like paleobotany to understand the floral events, like they have identified the species of wheat and barley, and also how they were kind of exploiting the climatic regime also. So they have also identified the use of red ochre application on the body of the human body. So that is another very fascinating aspect. And coming to the long distance trade, I mean, these have been excellently documented in Mehergarh by the French Archaeological Mission to Pakistan, by Jean-Francois Ayarij and his team. They have identified from Mehergarh some burials having jewelry, this kind of jewelry, and different kind of materials came from different parts. For example, shell came from the Gulf of Kutch and Karachi coast. Another type of shell, the Engina mendicaria, came from Makran coast, and Madras from Oman coast. Turquoise from Central Asia, and lapis lazuli from Afghanistan. So this is a long distance trade which was successfully garnered and replaced by the Mehergarh occupants nearly 7,500 in the 7,500 BCE. So this is the context of that actually paved way in the emergence of the Harappan civilization. So these are some of the ornaments found in the graves that indicates long distance trade. So jumping directly from the Mehergarh context to the Harappan context, as I indicated, the field work carried out by various agencies in the Indian subcontinent. It has brought to light nearly 2,000 Harappan sites, and these sites are well distributed. I mean, if you can see, they are located all along the Indus and its tributaries, and another river system which was flowing directly parallel to the Indus system, which is identified generally with the river Saraswati. And these bigger dots, they indicate the urban centers, the metropolitan cities of modern day equivalent, one can say. They are Mohenjo-daro, Lakhanjadaro, Ganveri-Malla, Harappa, Rocky-Gadi, and Dholavira. So these are the 6 largest Harappan cities. They are located at crucial locations so that they can garner the raw material resources located all around. And if we look at the settlement hierarchy, they had larger cities followed by smaller cities, and the yellow dots may be larger towns, and again the smaller towns located by the red dots. So this is the kind of hierarchy what we see in the context of the Harappan civilization. And now, thanks to the radiocarbon chronology, we have a very good chronological framework of this entire civilization. And scholars working on this civilization, they have also identified the possible social networking system, how different cities could have administered a small hinterland, and that's how they have been located at many different parts of this entire Harappan domains. Remember, the entire Harappan civilization is nearly 1.5 million square kilometers. So this is one of the largest occupied area. And another very important discipline which has helped in understanding the context of Harappan sites in relation to the dry riverbeds in the remote sensing. Starting from 1970s onwards, remote sensing has helped a lot in understanding and also tracing the dried up riverbeds. Here in this context, the large dried up river Saraswati was identified through remote sensing techniques, and also it was under study since the 19th century by Oldham. Two different Oldhams they have studied, and how they have hypothesized the capturing of the Sutlej river system by the Indus river system. So this is a very important contribution by the remote sensing studies, and it is still helping us in identifying the various dried up channel. And also interestingly, many of the Harappan sites located in Haryana, Punjab, Haryana, Rajasthan, and Cholistan region of Pakistan, they are located just on the dry riverbed of Saraswati, which is identified with the modern day Ghaggar Hakra river system. So the Harappan civilization came to light in 1924, but since 1980, only 2 sites have been inscribed in the World Heritage List. Mohenjo-daro, it was inscribed in 1980, and very recently Dholera was also inscribed in the World Heritage List, which adds much more value to this Harappan civilization. So thanks to the study by various scholars, in particular, I would like to mention about Randall, who has done a remarkable study in understanding the procurement network and redistribution network in the context of Harappa. Later on, collaborating with us, he also studied the raw material procurement network of Dholera, which is located in Gujarat. So from this study, we could know how different regions are having different kinds of raw materials, and how they might have been procured for the urban center like Harappa, and how certain raw materials are located in distant regions like Gujarat. This agate cornelian, the red colored dots, they are agate cornelian. They were procured by sites located very close to these raw material resources like Lothal in Gujarat and Dholera in the northern Gujarat, and ultimately they contributed to the overall trade network. So in understanding this, there are a lot of scientific techniques were used depending upon the kind of material for identifying the copper resources. Lead isotope analysis were used, and for identifying steatite, XRF techniques were used, and different kinds of techniques were used for understanding different materials, and ultimately the provenance could be understood and established. And this also helped in understanding the overall trade network that existed during the 3rd millennium BC. There were internal trade networks which kind of connected the Harappan cities with one another, and there were external trade networks, land routes that were connecting the other civilizations located in Iran, Central Asia, and also the Mesopotamian civilization. But another major marine network which also existed that connected the Harappans with the Mesopotamians. We will come to that later on. So understanding some of the very important aspects, some of them are very basic. There is no requirement of any detailed scientific analysis, but just a visual examination, like this kind of grinding stone fragments. Grinding stones contributed a very important aspect of the human life during the Harappans, because they have to grind the flour, grind the grains to obtain flours to make bread. So it is a daily activity. So each and every household, they had a grinding stone, they had some sort of a hot stone to grind the grains. So in order to have a hot stone, we need to find the stone material that has a considerable quantity of quartz in it. And in this context, the Harappans discovered this particular quartzite from Delhi, near the Delhi region, belonging to the Delhi quartzite family, from a hill known as Kalyana in Haryana. So from there, it was procured and it was distributed to many of the sites in Haryana, and ultimately it found the way even up to Harappa, which is located 400-500 kilometers away from the raw material resources. So this is the kind of location where the raw material is procured. Then it is found in many of the settlements in this part of the region, and it was reaching ultimately to Harappa. And another stone also they procured from the footings of the Shivaliks. It is a grey colored sandstone, which is also equally hard enough to for grinding some of the important grains. So this was also reaching to different settlements, and ultimately many of them reached to distant parts also. So if you look closer, one of the regions of the Harappan domain, that is the Gujarat region, it is very rich in, it itself is very rich in raw material resources, or it is also located closer to the raw material resources. So if you see some of the raw materials, they are copper, agate carnelian, which is a stone used for making these kind of beautiful ornaments, and limestone they were making using limestone for making these kind of pillar elements, particularly for Dholavira. And stearite was also available here, which is not of high quality as that found in the northern region, but still it compensated to a larger extent. Also, there are deposits of lead and silver in the Ambaji region. So all these things were exploited by the Harappans in Gujarat, and this could be also identified through scientific analysis. So one of that is again using the scientific analysis of lead isotope studies, through which it was found that the Ambaji mines, which is now defunct, it contributed a lot for the copper remains at Dholavira. So the raw material at the Dholavira, the finished product at Dholavira, it was analyzed along with the raw materials at Ambaji, and they were all matched together to find out that they came from the raw material. So similarly, if we look into the banded limestone, which is available plentifully near Dholavira, Dholavira is located on an island, which is a Jurassic period limestone formation, where bands of banded limestones are available in plentiful, through which they manufacture this kind of beautiful pillar elements. It was found for the first time at Dholavira in a context. Otherwise, it was found earlier from Harappa and Mohenjo-daro in a secondary context, and it was not understood properly. But now, when they found it in its original location, it was understood that they were indeed pillar elements. So, a normal pillar element consists of a square base with a biconcave pillar element followed by two biconvex pillar elements. So, over that, the wooden element came. Interestingly, very close to Dholavira, they found a quarry site where unfinished pillar element, they were still remaining there. It was left by the craftsman nearly 4,500 years back, and it is still lying there. So this is a remarkable finding, and analysis again from the site and from other findings from Harappa and Mohenjo-daro, it clearly indicated that indeed the banded limestone was quarried and manufactured from Dholavira, and they were carried through the river, through the boats. I mean, remember Dholavira is located on an island, so from there they have to cross the runoff. Then they might have followed the river road, and they might have transported this to over 1,000 kilometers up to Harappa. They also used remarkable technology to excavate this kind of larger resources. We have heard about great baths of Mohenjo-daro. This huge reservoir is 1.7 times larger than the Great Bath, and you can see the measurements. It is cut into the bedrock, and the undulations were filled with the stone blocks scooped out of this rock mass, and they were filled beautifully. So this is the southern series of reservoir where 5 reservoirs are found, and this is the central one, and 2 reservoirs on either side. The first reservoirs, they were used basically for sanitation chambers, so that they can allow the water without silt to reach the central reservoir, and the spillover, it reached the other 2 reservoirs. Similarly, on the eastern side also, there were larger reservoirs. So all of these clearly indicate the kind of water harvesting techniques the Harappans had, particularly at Dholavira. Interestingly, inside this eastern reservoir, they dug another step well within that within the reservoir, so that they can reach the water during the lean periods, reaching up to the water table and exploiting the water available during the lean seasons. And incidentally, this could be the earliest step well of the Indian subcontinent, and they date back to the Harappan period. So one of the important inside this is technologies also have another steps were locked within that Mesopotamia within the big reservoir, so that they particularly the Gujarat Harappans during the lean periods reaching up to the water level, they had a better material to perforate them. Particularly the artisans at Kambat is an artisan from Kambat. Pratap Bhai, he uses a diamond tipped drill bit. You can see the metal drill bit here at the tip. He places two very tiny diamond granules and fitted in a wooden shaft, and he operates it using a bow drill. The Harappans they did not know about the diamond and used instead a different material known as ernestite. I mean, again, it's a stone. Its geological provenance is unknown. Some scholars say that it was manufactured by the Harappans. They could have heated different materials and could have obtained this material, but still it is enigmatic. We are unable to understand. But the XRD analysis, it indicates the mullite and sillimanite phases, which indicate that the material was heated up to 1100 1200 degree centigrade, during which these form. So from this stone raw material, they manufactured these kind of drill bits, which were fitted in wooden shafts and mounted in a similar arrangement. The water from this part, it drips so that it cools down the bead as well as the drill bit, where it generates a lot of heat. So this is the kind of technology which the Harappans developed, and remarkably they monopolized the bead manufacturing technique during the 3rd millennium BC and exported them to Mesopotamia. They produced this kind of remarkable jewelry. We can see the red color stone with a white color decoration, which is again very unique to the Harappans. They also manufactured this kind of longer beads, often reaching to 4 inches and 5 inches in length, which formed part of a large waist girdle meant for the ladies. I mean, you can see this is the complete specimen from a site known as Aladino in Pakistan. 2 more specimens are known, one from Harappan, one from Mohenjo-daro, and they were worn by the ladies. You can see this is a figurative representation of a terracotta figure from Mohenjo-daro, where the waistband is shown. So what kind of mechanical process the drill bit undergoes, and we did that documenting it with a USB microscope, analyzing the tips, what kind of modification it goes through, and we also try to understand the different types of tips before it was put into use. So once it was put into use, you can see how they can undergo the change from a flattish top to a truncated top to a roundish one to a dimpled one, and more cavities formed inside one because of the rapid movement inside the bead, as well as the accumulation of quartz particles, which itself are very hard, and it creates a deep mark inside. And at this point of stage, when it could not withhold much pressure, ultimately it gave away and it broke here. You can see this is the final stage of a drill, where it broke away, split at the exact center of the tip because of the rapid movement and also the tightness which we experience inside the bead hole, and also sometimes it was snapped exactly at the center because it was stuck inside and it could not move anymore. So this is the kind of complete history of a drill bit one can understand, starting from the material, its composition, its mechanisms of drilling, and ultimately how it was broken. So this is one such very interesting study which we undertook at Dholera, and this could be very easily comparable with the modern day bead activities, bead manufacturing activities at Kambat. One can see the chipping of stones here. A craftsman sits here and chip the stones. They polish it here to make it very smooth and shiny. They also heat the agate carnelian so that they attain the typical red color. So that was the most sought out color, and the Harappans understood and they heated. And they initially traded inland. So they obtained the raw materials from Ratanpur, Marlagbet, and Khandek, all located in Gujarat. They went to different locations like Nagwada is one site, and Dholera, and from there they were redistributed to various other locations. So all the agate carnelian from Chandradodo, Mohenjo-daro, Nausharo, Harappa, and Rakigadi is 1,300, 500 kilometers away from the raw material resources. So all these raw materials, they were reaching these distant cities And now that could be very easily understood based on visual observation, based on scientific analysis, provenance studies that goes well into the understanding the mineral characteristics of these materials. So this is how science has helped really in understanding various objects used by the Harappans. And another very important object is the ceramics, because ceramics, they are found in thousands. It is the ubiquitous material found from any archaeological site. So this is the kind of ceramics which was used by the Harappans, and they are from different contexts, from burials, from habitations, and also they are very good chronological markers. For example, Professor Mark Neuer identified this particular type of goblets. We can say it's an equivalent of a pullard, which was disposable one datable to around 2100 BC, so that has a clear chronological marker. So these ceramics, they are also studied to understand their painting designs, how they were produced using Raman spectroscopy. One can understand what kind of minerals they were using, and you can see it's a combination of manganese and also red ochre, various colors of ochre as the base. So different information about these metals can be very easily identified. And now with the emerging technologies, scholars are working on these ceramics to understand what kind of materials they were used for cooking or storing, whether they were used for cooking meat products or vegetables. All these kind of things can be understood by taking a very minute fragment from the interior of these vessels and doing the liquid analysis using GCM, gas chromatography, mass spectrometer analysis. It clearly gives an idea about what kind of materials, what kind of stuff they were using for cooking and also for storing some of the materials. So another very important aspect is to understand the mineral character of the clay used in the manufacture of the ceramic. So the clay, along with the many additives, they can be very easily identified. If not the clay, but the additives, they can be very easily identified like these minerals. One can see from this image, different kind of inclusions were used, sand grains were used, so one can identify the quartz grains, the plagioclase feldspath, and muscovites can be understood. So various kind of minerals can be understood, and one can see the orientations, the grain size. All this gives very clear idea about the manufacturing techniques, and to a certain extent the provenance of these materials also. So this ceramic petrological studies, they really help in understanding the ceramic technology of the Harappans, also in different time periods also. And similarly, experimental archaeology. Once we know what kind of ceramic the Harappans used, what kind of paintings they were using, what kind of materials they were using, so we can replicate them and try to understand the exact technology. So that's what we also try to do. This is one such experimental study, and this is the kind of range of ceramics which we could produce using this experimental studies. And there are several other areas like paleobotany. It is one such very important science that helps a lot in understanding the paleo diet of the past populations. Here, in one such study, the microscopic phytoliths, they are quartz particles from different parts of the plant, from stems, from leaves, from different parts. Since it is silica, so they are preserved for a longer period. So for each plant species, so they are different, they are morphologically different. So understanding the morphology, understanding the species, one can reconstruct the entire floral data of the grains. These are the actual grains from the archaeological context, wheat and barley, and also lentils and rice and jujube. So these are accidentally fired, so they are preserved very well, and they can be used in understanding the paleo diet of the past populations, which have been done in some of the sites. And another area is understanding the bone remains. It's archaeozoology. The specialist zoologists, they study the bones from the archaeological context and try to identify the species when it was killed and were used for the meat production. All those stuff can be understood. So this is a complete front limb of a cattle from a site known as Karanpura. This is a mandible. This is a rhino bone. This is very interesting. Like this is a site from Rajasthan where the rhino bones have been found, and also shell remains. These are the shells, freshwater shells. So different dietary practices of the past humans can be reconstructed. Similarly, what kind of textiles, I mean, how they were dressing themselves. I mean, we can't find the actual textile remains, but from these kind of tools. This is a spindle hole which was used to separate the thread from a cotton or wool. So this was used, and this is how they were used. They were inserted in a wooden shaft, and they were rotated using the to and fro movement, and the thread could be separated from the cotton or wool. And interestingly, these 5 objects they are formed from a site known as Karanpura, where they have a typical Harappan symbol, also maybe clearly indicating a ownership record also. I mean, this is clearly a very good example. And another example is that from the copper objects, if they are buried, or if they are found in the context of textile remains, organic remains, they tend to preserve them in a better format. Again, this is from Mehergarh, from the Neolithic context, again from thanks to the French archaeological mission to Pakistan. So they have found a copper bead inside which they have found the remains of cotton thread. So this is a clear indication of how cotton was present there nearly 9,000 years back, and it was also used to thread this copper beads. Similarly, we did an analysis from Dholavira. This is a broken bead from Dholavira, inside which we found some thread remains, and it was analyzed in the scanning electron microscope. It also turned out to be cotton or jute. I mean, it is not finally identified because there are difficulties in identifying the ancient ones, because the morphology changes a lot when we compare them to the modern context. There is a slight difference. So this has been tentatively identified as either cotton or jute, but the most important aspect is that one can see the actual remain of a textile, the thread actually used in a bead datable to nearly 4,200 to 4,300 years back. So we can also study various aspects of the Harappans. I mean, not only Harappans in any different time period, but particularly in the context of Dholavira, the kind of ratios and proportions they have used in planning the city. And each division of the city and overall planning, it clearly indicates certain ratios and proportions. You can see either they are 1:1 or 1:2 or 4:5 or 6:7. So different parts have very good ratios, and they were executed through a very good planning. Also, if you can see, the most important component of the Dholavira, it is well fortified with thick walled and multiple levels of entry checkpoints, which clearly indicates that the persons living inside were very important. And most interestingly, the gates with these elaborate pillar members, they are located only here and nowhere else. You can see some of the closer details of the gateways, which was used to enter into this very important part of the settlement, and which incidentally had these kind of stone pillar elements. And also they had a unique system of burials where a huge earthen tumulus was erected over the burial remains, but no skeletal remains were found, only evidence for elaborate ritual things. And interestingly, this kind of tumulus burials from Dholavira, it has its parallel with some of the royal burials from Bahrain, located in the Persian Gulf. So we also come to know about various aspects related to the human burial remains, the disease pattern. All these things can be understood again by expert opinion or expert analysis by anthropologists. So there is a branch of archaeology dealing with the human remains and using most sophisticated analysis nowadays available, like you can do the stable isotope analysis to understand the past migrations, because of the characteristic strontium and lead isotopes that is drawn from the earth, from where the humans were living, because the geological deposits, they all contain strontium and lead, and they vary from region to region, and that is well known and mapped all along the Indian region. And wherever we live, we consume the plant as well as the meat products, which in turn draw this strontium and lead from the geological deposit. So this is preserved in the human tooth very well, and the tooth can be analyzed and due to the variations in the composition of strontium or lead values, one can easily identify to which time period they belong to. So this is an analysis which we did for Sanoli. Sanoli is one of the largest ceramic complex in the Indian subcontinent, and analyzing the first, second, and third molars, we could reconstruct who were the locals and who could be the non-locals. Non-locals means they might have been located 50 kilometers away, 100 kilometers away. They could have moved here, and that could be easily understood from the concentrations of the lead and the strontium. So this is one very interesting area along with DNA, which can clearly indicate how the humans might have moved from one area to another. Similarly, there are evidences that the Harappans moved to the south, the southern part of the modern day Iraq due to the trade activities, which is clearly mentioned by the cuneiform records. The written records of the Mesopotamia, written in the cuneiform script, they mention about Dilmun, Magan, and Meluha. Dilmun is Bahrain and its adjoining region. Magan is Oman Peninsula, and Meluha is most probably the Harappan civilization. Because these kind of ornaments which are produced in the Harappan civilization, they are found in Mesopotamia, and we have a complete list of what kind of objects the Meluhans might have. So that interestingly, the mention of timber is there. I mean, that is very, very interesting, because the Mesopotamians, they were actually searching for timber because the entire region is devoid of any forest. And interestingly, the Meluhans or the Harappans, they could have supplied the timber along with these kind of very beautiful ornaments. So if you look at the overall context of the Harappan trade, they were participating in an international trade mechanism that can be equated with the world system theory at that particular point of time. Their products are found in all parts of the Western world at that particular point of time. And these all can be understood using all scientific analysis. We can do the provenance studies, we can do the technological studies of these important products. We can also understand the various manufacturing technologies. So in a nutshell, the sciences today, it's helping the archaeologists to understand the humans in a better manner, how they were living, how they were manufacturing, what kind of technologies they had, what kind of diet they were having, how they domesticated, and how they interacted, and even they migrated from one region to another. And remote sensing also it is helping us a lot in understanding the past landscapes in a better manner, and also to identify new sites also. So that is another area where remote sensing also helps in a better manner. And with this, I end my presentation, and thank you very much for this, for hearing me. And if you have any questions, any queries, please mail to me so that I can answer them. Thank you very much.
Thank you so much, Dr. Prabhakar, for sharing with us the insights about the Harappan civilization. Definitely, by knowing about our past, we can improve our present and plan for the future. Our second speaker for this function today is Dr. M.B. Rajani. Dr. Rajani is an associate professor, National Institute of Advanced Studies, Bangalore. She received the Ratchapuri Kamakshi Memorial Young Geospatial Scientists Award 2011 for her PhD work. She is a member of Indian National Young Academy of Science from 2018 to 22, a young affiliate from 2019 to 23 of the World Academy of Sciences, and a recipient of P.R. Pisharotti Memorial Award in 2019 by Indian Society of Remote Sensing. Dr. Rajani's research has two interrelated facets. First is analyzing the cultural landscapes using geospatial data to identify new features of archaeological interest, and advancing the usage of such analysis for preserving built heritage in the face of rapidly growing infrastructural development and urbanization. Her findings based on remote sensing analysis at the site Talakadu were confirmed 8 years later through conventional excavation, and her analysis of Nalanda has revealed the larger archaeological expanse around the protected site. Her recent book, Patterns in Past Settlements, a geospatial analysis of imprints of cultural heritage on landscape, aims at imparting this knowledge to larger research and academic communities. Today, she will be talking about archaeological investigations using remote sensing technology. I request our team to please play Dr. Rajni's session.
Good morning. It is indeed a great pleasure to speak on the occasion of National Science Day, marking the discovery by our Nobel laureate, Sir C.V. Raman. I'm indeed thankful for the organizers of this program for inviting me to give this talk. As the title of the talk suggests, it is archaeological investigations using remote sensing techniques. So without much of further ado, I will start my talk. I'm really sorry I'm not here live to speak to you because right now I'm, or rather when you are listening to this recording, I'll be on field with remote access, and therefore I thought it would be better to record and send you this. Thank you very much. As you are all aware, remote sensing is a means of sensing and gathering information from a distance. And the application I work on is archaeological investigation. With or without our consent, details from our daily lives are being captured and stored in vast digital databases. If humanity were to vanish tomorrow and alien historians chanced upon these databases centuries hence, they would have incredibly rich resources for studying humanity's past. As humans in 21st century trying to understand our past, we have no comparably detailed database to tap into. Instead, we must scavenge for traces of past human activity that have survived in material form and develop expertise in interrogating these material before their secrets fade into oblivion. To scrutinize written records, we turn to historians. We rely on archaeologists to scrutinize ancient materials ranging from small-scale fragments of pottery, jewelry, bone, and brick, or large-scale artifacts such as individuals, buildings, or whole settlements. In each of these domains, scholars have benefited from scientific developments that are constantly expanding the kind of ancient materials that are interrogable, and the technological advances that enhance our ability to extract useful information from them. Remote sensing contributes to a branch of archaeology that scrutinizes landscapes, such as this, for instance, at Nalanda. Humans necessarily scar the landscape when they construct structures such as forts, canals, tanks, and road networks. These scars, which can survive for many centuries, are also material records of past human activity and therefore worthy of study. However, these scars are difficult to discern at ground level, and their value was largely unrecognized until they were observed from an aerial perspective, initially from aircraft and more recently from satellites. Lieutenant Colonel Beasley, a sapper of the Royal Engineers in Mesopotamia during World War I, spotted distinct outlines of ancient canals in the course of his repeated flights over the then enemy territory, Tigris and Euphrates plain, while carrying out a survey of contested area beyond Baghdad. He wrote, "The remains of an ancient city were disclosed, which would otherwise have been not discovered in all probability." This was Old Samarra. A more recent example here is the false color image of Bangalore. And here is a map made of Bangalore in 1791, which shows a four-cornered settlement and an oval citadel on the south. If you carefully analyze the satellite image, we can identify where exactly the old settlement lay. we can still see the pattern. Apart from such images, analysts can pull together spatial data from other sources, including old maps, painting, textual reports, and field surveys. Here is an example of Kollam in Kerala. The first two maps were made by Portuguese, and the third one, 1687, was by the Dutch, and the later painting showing the bay. So you wouldn't imagine the third map is the same area of the first two, but a close examination will give us enable pointing at common locations. Here is a picture from ground of the only building that survives. Here is a satellite imagery which gives the context of the only remain and also context of what was the Dutch extent and what was the Portuguese extent. This coherent spatial view allows an analyst to hunt for visual patterns in a landscape in a manner akin to an art historian examining a painting through an appropriate historical lens. Furthermore, just as a modern art historian uses technology to scrutinize what lies beneath the topmost layer of paint, advances in technology of remote sensing permit satellites to view landscape in different wavelengths and reveal hidden layers of human artifacts. The purpose of such analysis is to identify and understand, conserve and protect remnants of our past. While all these sites that I have worked on is situated in the Indian subcontinent, my research has helped me recognize and articulate universal principles that I'm excited to present here. The first idea I would discuss is landscape archaeology, the role of remote sensing and GIS. The primary focus here is on built heritage that have made marks on the Earth's surface in the process of being built or modified. These structures constitute the known remnants of built heritage at a site, and it is possible that hitherto unknown remnants associated with site still exist in its vicinity. Consider the vicinity of Nalanda, for instance. When we visit the site protected by Archaeological Survey of India, we see these sacred temple structures called chaityas. There are 6 of them, and there are 10 dwelling structures called viharas. Each has a central hall surrounded by monastic cells. Infrared image shows the protected site of Nalanda and the area immediately around it. Notice how 4 temples marked in blue in the protected region lie in regular intervals along a straight north-south line. If Nalanda had more temples, one might expect them to lie further along the line. Sure enough, the infrared image suggests that the presence of an unexplored mound to the south and one unexplored to the north. In the north, one can also see crop marks at exactly the intervals we are expecting. The central thesis of my presentation is that a careful study of site's vicinity or spatial context can lead to 2 important types of discovery that may improve our overall understanding. That may improve our overall understanding of the site and inform our strategies for its protection. Firstly, the discovery of further instances or attributes of built heritage, and secondly, the discovery of artifacts such as former water bodies, canals, and mounds associated with past human activity. Next idea I want to discuss is landscape morphology and spatial patterning of archaeological signatures when viewed from above. By viewing a landscape from a vantage point of aerial or space platform, one is able to observe how landscape evolve over time and also get a sense of the implications of the evolution to the analyst seeking to identify archaeological features from above. For instance, the well-known example of crop mark in fields, such as this, first observed in aerial photos of World War I and II, turned out to be surface impressions of buried fort wall and adjacent moat, such as these diagrams depict. But this is only one of many different ways a landscape can morph itself, which depends on what has been happening subsequently on the surface. Even in urban jungle-like cities, one can see traces of past layout which are inscribed as road or land use patterns. A ruined, disused wall becomes hindrance in mobility, and people and goods move along it, creating paths which over time become roads and remain as a permanent scar, even if land use changes on either sides of the feature. For instance, let's take an example at Old Delhi. Jama Masjid and the Red Fort are easy to identify on Google Earth image. Lal Killa was the citadel of a much larger fort encircling Shahjahanabad, which no longer exists. But can we still see its scars? Let me cheat by overlaying the satellite image with a 19th century map of Delhi, which shows the surrounding fort wall. Now I hide the map, and suddenly you see where the fort lay. This is an example of how a site looks in an urban area. In most cases, there are roads built adjacent to fort walls, as the previous diagram displayed. Similarly, the manifestation of sites of different kinds of land surfaces vary accordingly. When I was writing my book 2 years ago, I wanted a term to refer to the landscape in the vicinity of a site. That included area that affects the site as well as area affected by the site. Since none of the existing terms seemed suitable, I called it spatial context. For a given site, we would like to identify features in satellite image of its spatial context that may provide new archaeological insights for that site. When we look at a site's spatial context today, we see only the present point in its evolutionary history. For some sites, we have historical spatial records that provide multiple snapshots for the spatial context as they change over time. These records may date from a few years ago, such as Google Earth images, to a few decades ago, such as other older satellite imagery and corona satellite imagery, to a few centuries ago, example, old maps, paintings, and spatial description in historical texts. Even with multiple snapshots for a site, our data is generally too sparse to precisely infer the sequence of gradual changes to its spatial context. This lack of data forces us to guess how the spatial context evolved and to use these guesses to explain why we can or cannot observe certain features. Images may directly show certain surface features, while some subsurface features may only be visible indirectly through morphological expressions. For example, here is a 19th century map of Lal Kot and Kila Rai Pittura in Delhi, which shows the spatial layout and shapes of the fort wall. Then, image of 1965, which shows quite a bit of the fort wall of a site that was active in 12th century, and then a recent image where most of the land use over, along, and around the fort have been changed. In most cases, recent image is what we have, and we have to hypothesize the reverse order, which is sometimes aided by old image, maps, records. Thus, understanding the landscape morphology and spatial patterns of sites provide the basis for answering critical questions such as what kind of feature should I be looking for in a satellite image, and why can't I see what I'm looking for in this image. The next idea is the science and technology of remote sensing in the context of archaeology. There are various types of imaging technologies that are operational on contemporary and retired Earth observation satellites. Understanding these help the analyst to answer the question, is this type of satellite image likely to be useful for my analysis? For instance, look at these images of a landscape of Belur in Karnataka. The one on the left is a false color image with infrared band. It shows the circular moat that surrounded the old settlement, whereas the natural color image on the right, though of higher resolution, doesn't show the circular pattern clearly. Understanding the science behind technologies help in answering the inevitable follow-up question, why and why not? Here, I quickly demonstrate how the natural colors that fall on, here is a leaf section to show how the natural colors, red, blue, and green, interact with the surface layer of leaf, whereas infrared diffuses, and therefore we see a higher reflectance in infrared band, and this aspect can be also used to identify buried archaeological pattern. The next idea is GIS, an array of tools for archaeology. GIS is an associated technology that is used for analyzing Remote sensing images by itself is like a photograph, but bringing images to a GIS platform fixes the image to its coordinate, doing which enables overlaying multiple layers like maps, images, field records, making measurements, analytics, and extracting information from them. I am quickly going to discuss a few case studies. I briefly illustrate 5 case studies to demonstrate that there are no fixed answers to the question, how should I conduct geospatial analysis for my site? This is to re-emphasize the core ideas in the themes discussed earlier in more complex settings. In our experience, there is no fixed or formulaic approach to geospatial analysis of archaeological sites because the process of analysis itself is sensitive to variations between the sites. These variations can be grouped into 5 groups. Variations in the features of interest. These will vary across the site in terms of their scale, their architectural styles. A Buddhist site will look different from a Mughal site. A Mughal site will look different from a Deccani site. A Hoysala site will look different from a Vijayanagar site, and so on. So there is the cultural patterns are different. So that's one variation. Variation in terms of natural setting and subsequent natural changes. Sites vary in terms of their terrain. They could be in flat plains, hills, etc., as well as their exposure to natural processes such as floods, weathering, so on. So that is the second. Third one, anthropogenic changes. Sites vary in terms of subsequent human activities and their impact, whether it is in the middle of a city which has been affected by growth of city or agriculture and so on. Fourth one, satellite imagery. Data from satellites may be plentiful on some sites but limited on others. And the fifth one, historical spatial records. A site might have been very well studied by historians and archaeologists before we take up, whereas some sites there may not be any past work on the site. The purpose of this discussion is to illustrate how the process of analysis responds to these variations. Thus, we have carefully chosen 5 sites so that there are significant variation across these sites in each of the 5 categories. First one is Nalanda, which I already discussed. I discussed about it remains in the immediate vicinity of the protected site. When we look at a larger area, we also see there is a large cluster of water body, all of them squares or rectangles, with the sites addressing cardinal directions, which actually shows the extent of the old site. Apart from that, there is also a canal, a paleo channel indicating a past canal which connected a nearby river to the site's location, which also suggests that water was drawn through this means at some time. Agra, there is a map of Agra dating from 1720s, which shows 50 riverfront gardens. Today we only have Taj Mahal and Agra Fort and a few others protected. 50 riverfront garden and 2 tiers of city walls and a network of ditches. Again, using remote sensing and GIS, we analyzed, and though most of these riverfront gardens today don't exist or are urbanized, or some of them are there but not maintained, we were able to detect each one of them and also the 2 tiers of fort wall as well as the network of ditches. Lalbagh Palace Garden at Srirangpatna. Lalbagh of Bangalore is famous, whereas Lalbagh Palace Garden in Srirangpatna had gone out of living memory, but using old maps and some remains on the ground and also using old painting, we were able to identify the Charbagh layout of Lalbagh Palace Garden at Srirangpatna. Talakadu is a site that was originally capital of Ganga dynasty. And over time, it has been part of Hoysalas, Vijayanagar, Mysore Wadayars, and so on. So, and being in a hairpin bend, it also has collected a lot of point bar deposit, which has buried the site itself. But using remote sensing, we identified 4 features, and also this is the only site where we were able to collaborate with archaeologists to conduct some excavation on the location that we identified. Which was done, and as archaeological processes are quite tedious and take a long time, the excavation reports were finally published nearly 10 years after we had originally done the work. in 2009, and it was published in 2019. And the excavation also proved what we had found was correct. Last one is Mahabalipuram. So here what I did was to use an old map which marks 7 monuments around the coastline, and using those depiction of the monuments, I was able to identify the monuments, and also I was able to analyze that in 1670, when the map dates, the coastline was further inland, and the water has actually receded since then. So the next idea I'm going to discuss is site protection boundaries, a double-edged sword. So till now what I discussed is how we can use remote sensing to understand the past better. Now I'm going to demonstrate how it can be applied for protection of sites and so on in today's world. So far, I have given an example of how remote sensing shows the features in the vicinity of sites that were originally part of site. Therefore, if I ask the question, can geospatial analysis be used for preserving, conserving, and managing cultural heritage sites? The answer would be a confident yes. But let's see what is the practice as of now. It is very important to define boundaries to implement protection, because if one did not have protection boundaries, for instance, here is an unprotected site affected by widening of Airport Road in Bangalore. Here, an armory from Tipu Sultan's time had to be moved, spending crores to make way for doubling of railway. But see what having boundaries can do. Look at the amount of urbanization in the landscape of Bodh Gaya from the time it attained World Heritage Tag to now. One wonders, is this recognition really protecting the site? Therefore, site protection boundaries are a double-edged sword. If you don't identify boundaries properly and regulate the land use, then we lose them. We need to define boundaries for practical purposes for implementing protection measures, but an inadequately drawn boundary can become the cause for the spatial context of a site or the archaeological landscape to be damaged. The site can become a victim of its own popularity. For instance, Nalanda was tagged World Heritage by UNESCO in 2016 with a core and a buffer zone. But look at the expanse of its remains. One wonders, will this landscape see the same fate as Bodh Gaya in the next 2 decades? So remote sensing data analysis enables visualization of some of the limitation of current approaches, and more widely adopting remote sensing GIS in the practice, implementation, and monitoring can address these limitations. So there are other opportunities this area also provides. One is archaeoastronomy. So we can study archaeological buildings and measure their angle of facing, and we can connect it with astronomical explanation. Second one, we can use old maps, war maps, and identify things that are about those war. For instance, here is a map of Srirangapatna when Tipu Sultan had used rockets against British. So this map records where were British stationed, where were Mysoreans stationed, and did the rockets land. So using this, we could also measure the range of the rocket. And as already mentioned, we can use archaeological site location in coastal area, which can also give us information about how the coast has changed. So it contributes to other fields as well. There are 3 potential groups of users who can benefit from the kind of work I have presented here today. The first group comprises of students and budding or established researchers in the field of archaeology, history, and art history who see potential value in analyzing the landscape in their region of interest. The second group of users are authorities concerned with protection of cultural heritage. They are part of international organizations such as UNESCO, as well as national and subnational agencies. In India, these agencies include Archaeological Survey of India and each state's Department of Archaeology. Their mandate includes defining property boundaries for protecting archaeological sites and regulating changes to land use in their vicinity. Finally, non-government bodies and private professionals who are involved in making maps and master plans for cultural heritage protection and conservation. Adopting remote sensing would help users in this group develop more efficient and effective processes as they scramble to document and protect thousands of immovable cultural heritage artifacts before these are consumed by expanding cities, industries, transport networks, and other hallmarks of rapid urbanization. Here is a picture of my institute where I have been conducting all my research and also have developed a group. And thank you very much for your patience. And I hope you enjoyed listening to me.
Thank you, Dr. Rajni, for your interesting session. We are also thankful to you for agreeing for this session in spite of your busy schedule. Thank you so much. To take the archaeology from space to ground, we have with us our third speaker for today, Mrs. Shefali Agrawal. Mrs. Shefali Agrawal has obtained MSc in Physics with specialization in Electronics and PGD in Integrated Map and Geoinformation Production from ITC, the Netherlands. Ms. Agrawal has joined IIRS in India and ISRO. She has published around 50 papers in national and international journals and has also edited 2 books. Today, she will be talking about ground-based geospatial techniques, especially lasers for archaeological studies. Ma'am, the stage is now yours.
Thank you, Poonam. Are you able to see my slides?
Ma'am, we can see your desktop, but not the slides.
Okay, just a moment. Now is it clear? Are you able to see?
Deepika, the society office, can you please confirm? Yes, ma'am, now it is okay.
Okay.
Now again, the desktop is appearing.
Still?
I think. Yes, I think the active screen is not there. It is not the active screen.
It's the active screen. Wait a moment.
Yeah, for a moment it is coming, but the slide.
I have shared the entire screen actually. Let me do it again.
Yes, ma'am, it is now visible, but
Okay.
but it is not in the presentation mode.
I have put in the presentation mode.
Now it's okay. Now it's okay.
Okay. Thank you, Dr. Poonam, and thank you, ISRS, for giving me this opportunity to speak on the occasion of the National Science Day. The topic which I'll be talking about is LiDAR remote sensing for archaeology. So as you've been listening to the past 2 speakers who had been extensively talking about archaeological aspects, so the question every archaeologist would like to ask is, what did past civilizations leave behind? It's one of the very difficult questions to answer because the remnants of buildings and other sites can be impossible to spot due to the depletion in terms of wear and tear with time due to the natural phenomena, and can be covered, and the old walls can be covered, the foundation with trees, vegetation, water, soil, and many other aspects. So the use of remote sensing techniques have in fact aided the archaeologist to uncover the unique data that can complement or help them help them in traditional archaeological excavations to study the landscape in a better way. They provide opportunities for innovative investigations, that is mapping at regional scale, settlement histories, documenting ancient landscapes. land use practices, revealing the complexity of settled spaces, environmental and monitoring at-risk cultural heritage. So aerial photography was one of the oldest and most widely used domain of archaeological remote sensing. But as you saw from Dr. Rajni's talk, that space-based satellite images can be extensively used, specifically the multispectral and high-resolution optical images were effectively used by her for to understand the past and preserving the heritage sites, which can be coupled with the GIS technology to understand and also to complement, to assist in preserving the heritage sites. So primarily the use of high resolution satellites, thermal and infrared capabilities can help in identifying potential sites of interest in the Earth and find subtle anomalies on the Earth's surfaces. And but these optical remote sensing data which includes both high resolution, multispectral and thermal remote sensing data, have certain limitation. The impossibility of surveying archaeological features of areas which are covered by dense vegetation. As I said, that the past has been covered, may be covered due to dense by trees, vegetation. So these data sets cannot penetrate beneath these vegetation layers and provide information on that. The difficulty in detecting archaeological features related to the micro relief also is a case in case of bare ground surfaces, and the impossibility to characterize the anomalies in 3 dimensions. So though they have provided a large volume of information for archaeologists, but optical data sets have their own limitations. So to overcome these limitations, LiDAR is one of the tools which is helping the archaeologists in addressing all these challenges. So LiDAR, which is light detection and ranging, has in fact changed the face of archaeology by making it possible to measure and map objects and structures that might otherwise remain hidden. So it provides a remarkable surface detail. It provides you subtle anomalies, finer, minute details with absolute vertical accuracies to a few centimeter level, even in the vegetated areas, and horizontal sampling density well below a meter. So basically, it helps the archaeologist to document the landscape in the same way as experienced by people. That means in a 3-dimensional perspective. So that is, it provides visualization of these landscapes in a way that was never before possible. So LiDAR, as I said, is an acronym for light detection and ranging, is an active remote sensing technology. It involves, if you see from here, it involves sending of laser pulses from a transmitter, which is placed on a platform, and measuring the distance between the target and the sensor. So this distance is basically calculated by the time difference between the laser pulse sent to that received after reflection from the object. So this gives the depth information about each and every object on the Earth's surface. So LiDAR system basically produces 2 data sets. One is a precise position and orientation of the platform, which is obtained from the GPS, and the INS, that is the Global Positioning System, and the Global Navigation Satellite System, and the INS, Inertial Navigation System, and the distance which is being measured. So one is the position of the platform, and the other is the range which it is measuring, the distance between the object and the transmitter. So by combining these 2 data sets, one can compute the position of the object on the ground. So finally, what do we get is a point cloud, which represents the coordinates or the reflections from the ground with vegetation or any kind of artificial objects. So in comparison to the optical remote sensing, LiDARs provide a more detailed and a more positionally accurate information in a 3-dimensional perspective without additional processing. If we talk about traditional optical data sets where we use photogrammetry, which requires subsequent processing, but in this case, the 3-dimensional information is produced with a minimum processing aspects. Now, where there are various kinds of lidars are there, which are used in archaeology, along with their visualization and processing techniques, and they are classified based on the use or function, or on the platform they are placed on. So based on the function use, there are two major categories: topographic lidars and bathymetric lidars. Topographic lidars are basically used, they are on the Earth's surface, and they are mainly used in monitoring and mapping of topography of a region. So for landscape archaeology, to understand the features on the Earth's surface, topographic lidars are utilized. And bathymetric lidars are basically used to gather information from underwater. So these are used in measuring the depth of water bodies. The bathymetric lidars uses the infrared light, which is reflected back to the aircraft from the land and the water surface, while the additional green lasers are also there. It couples with two laser beams, one in the infrared and one in the green wavelength region. So the green wave travels through the water column, and it provides you the depth information. And bathymetric information is very crucial, where you have, like what talked about, to understand the coastal area changes in harbors and near shores and banks. And it also is useful in locating objects on the ocean floor. So based on the platform where they are placed, the lidars are categorized as airborne lidars, which I said was one of the oldest methods to study the archaeology, to investigate the historical landscapes throughout the world. They have been extensively used. Next is the space-based lidars, that is on the satellite platform. However, these the advantages of the space-based lidar platforms is because the airborne lidars are not available globally and not frequently updated due to its high cost per unit area. So space-based lidars are there, which can map globally, but energy requirements are limiting. Currently, there is a limitation in the space-borne lidars due to sparse sampling points, which is there, which are making it unsuitable for archaeological applications. There have been 6 space-borne lidar missions which had been launched, which are catering to various applications. Like for one is an ice cap for measuring the ice cap volume. ISAT from the US was launched. Then to measure the cloud and aerosols, Calypso, and to measure forests, height structures, forest heights and their structures, ZI was there. Then we have the drone platforms, which are somewhere. Then we have the terrestrial, before I come down to drone, the terrestrial lidars, which are being used to get detailed information of the features. Basically, they are used for scanning specific features like buildings, monuments, where you want, and there are examples where they have been also used to scan a complete site, but specifically they are more useful where they provide a very in-depth, detailed information about a monument or a building. So these ground-based terrestrial lidars can be installed either on a tripod or on a moving vehicle, so they can be static or mobile. So and it collects data points that help in a very highly accurate identification of features. And the mobile is generally used, mobile-based platforms are generally used to analyze infrastructure or roads, whereas the static lidars are more preferred, handy to use, and are used for in the applications of mining and archaeology. The new platform which has come up is your drone platforms in the last few decades, because of the development in the sensor technology, the lightweights, and the drone has become a very popular platform which can fly at an altitude of few hundred meters and give you a dense network of point clouds, and is very useful for archaeological applications. So if you can see from here that how with the different kind of instrument platforms, the density and the area coverage varies. So satellites gives you a large area coverage, then you have an area platform, then you have these air-based platforms, drone and the ground-based platforms are morely in conjunction to each other with the mobile-based laser scanners and the ground-based laser scanners. So the area coverage reduces as per the platform, and the density of and the accuracy of the points is higher with the ground-based platform in comparison to the space-based platform. So this is another table which shows you the different kinds of space-based platforms, air-based platform, drone, and the TLS with the kind of accuracies which you can achieve. So the altitude of a space-based platforms are around 600 kilometers. The airborne is around kilometers. Then the drones is from 50 meters to 500 meters, and TLS is basically on the ground. And the footprint, the point density which you can calculate from this is the 1 point which transmits is having a radius of 7 meters to 60 meters in a space-based. Airborne, we have around 20 centimeters, drones from 10 to 20 centimeters, and TLS is around 1 centimeter point in footprints you get. And the vertical accuracy accordingly is in the range of 15 centimeter to 10 meter for space-based, 20 for aircrafts, and the drones again 5 to 10 centimeters, whereas the TLS is 1 to 10 centimeters, depending how the range, that is how far you have kept the instrument from the monument or the built structures. So the LiDAR produces a huge volume of three-dimensional 3D information that it contains basically the X, Y, and the Z coordinates of a point, and it is known as a point cloud. So we have this is a high density data sets where you have each, it's not a picture, whereas each is a point, collection of points where each point consists of 3 variables, X, Y, and Z. So this is enabling us to, it's transformed the way the archaeologists are using it to understand the past societies and the landscapes. So the LiDAR-derived data provides you a permanent horizontal and vertical document of everything on the landscape, like archaeological remains, vegetation, topography. So thus recording, if you record the status of site preservation, deforestation, modern construction at a single point in time. So you can do, based on this, you can use it for varied application. And as I said, the major strength of the LiDAR is to pinpoint tiny surface anomalies that indicate small sites like graves or the big ones like sunken cities. But LiDAR also has its own limitation. When we have a very dense network of vegetations, so it cannot penetrate, it's difficult to penetrate at densely wooded areas, and sometimes cause features to be missed out. So in those cases, LiDARs may not be very handy, but in general, if there is a vegetation with some kind of an opening there, then LiDARs can provide a in-depth information beneath the vegetation cover. So digital elevation model, which represents the shape of the Earth's surface, is one of the most important product of the LiDAR data. So it allows you it also allows you the acquisition of vegetation characteristics, as I said, the vertical profile, height, etc. And all these information can be used in the analysis of the past landscapes, since the relief, shape, and terrain characteristics are represented partially by the vegetation properties, which have influenced the settlement patterns and the land use. So with adequate data processing products or the images, which we can couple the images with the LiDAR data, we can reveal the anthropogenic features, both modern in terms of building, power lines, and those belonging to the recent and the ancient past, like agricultural modifications of the terrain. A variety of structural remains from different archaeological periods have been investigated using these data sets. So for example, many of the buildings and artifacts of Mesoamerica's civilization have been hidden by a lush rainforest vegetation. So LiDARs has helped these archaeologists to unearth these hidden gems beneath the dense vegetation cover. So LiDAR has been used extensively by basically the airborne LiDARs to uncover the ancient Maya buildings, roads, and other features of this civilization, and even create a three-dimensional map of a Maya settlement in Belize. Another example, if I say the ruins of Mahindra Pravrata, a 1200-year-old city in the Cambodian jungle, uncovering the sprawling, highly structured settlements, has helped in, uncovering the sprawling, highly structured settlements that would have been remained hidden from the satellite images or ground surveys due to the heavy jungle canopy. Another study was related to the North American area where they used LiDAR data in conjunction with archaeological data and GIS platform to study the hydrology and agricultural practices of the prehistoric historic Hohokam in the American Southwest. Because of the three-dimensional products produced by LiDAR, it was possible for them to model the flow of water over the landscape and to demonstrate that prehistoric rock alignments were used to modify both the channel and the surface flow of water. So it's not only the, you can analyze the entire how the hydrology or the drainage systems were there in the past. So LiDAR data not only helps in understanding the domestic architecture, but also enables the study of hydrology and water management system used in the past in a greater detail, and which was probably hidden or now camouflaged by the dense vegetation cover. Another example which is there was LiDARs have been was used to spot more than 20,000 archaeological features of a minor site in Mexico that actually had been home to an ancient city. So the LiDAR data could easily, unravel or reveal what was hidden in just a 40-minute flight they had in that area. So in just a 40-minute flight time, they collected the data and they could reveal what was hidden beneath it. So while airborne LiDAR scanning has been effectively used in many studies in archaeology, which I've already highlighted to you, there were many more examples. I just picked a few. It is suitable, it is able to use, in a very, when the area is, or an expansive scale is large, the ground-based methods capture the landscape anomalies or depressions from the cultural features that have remained invisible to the naked eye in a very finer details. So when a very high level of detail is required, like building level detail from elevation information, one needs to create a fly-through, wants to have a realistic look like images or a 3D models. So these ground-based instruments are much more handy. They can be used to produce a building information model of historic buildings, because terrestrial laser scanners, they provide you 3D they can help you in creating a 3D documentation of the heritage sites, which can be utilized for preservation and reconstruction in case of any damage due to natural or man-made phenomena. So as you can see, the terrestrial laser scanners or the ground-based LiDARs, they provide you an accurate representation and help you in creating a 3D documentation of the heritage sites, built monument structures. So what is the benefit of this 3D documentation? It can help the archaeologists answer few queries, like how quickly a feature is changing. Because laser scanners can record in detail where a feature, structure, or site might be lost or changed forever. It can also help to understand how one feature in the landscape relates to another. So what is the proportion of an institution's ground to its built structure? Based on the contour of the landscape, how will sea level rise affect the estate over time? So these terrestrial laser scanners can help inform understand the overall cultural landscape, how it has fashioned and how it compares to the surrounding landscapes. The another aspect which can be addressed using this 3D documentation is the size of the structure. Since these laser scanners provide pinpoint accuracies regarding dimensions of objects and structures, they can be useful in planning for preservation projects by creating a record before renovation of a structure or landscape. Then it can help in improving the accessibility, like for trawl structures, a frieze, tilling, or other archaeological detail may not be entirely visible from ground, like it's tilting or whatever, may not be visible from ground level. There may be environmental barriers, there may be some obstructions, and many times in museums, objects are blocked from inspection and even from touching. So a 3D scan can replicate the proportions and form on an object for access on digital platforms. It can aid an expert in understanding the element of an object or a structure, and it because you can zoom in and enlarge it as and when required on a unlimited scale. You can zoom it and try to analyze the details in an unlimited way, provided. And it also can help you in improving the engagement with the general public. So the models which you create from this, you can use it for creating a virtual museum, virtual digital tour for mobile devices. For mobile devices, you can allow the public to manipulate, enlarge, examine objects. You can create a complete three-dimensional perspective, a virtual tour of the monument area. Then also it can help in replication of a model. So the accurate model is useful for, this can be utilized for producing a replica for display or as a replacement in a restoration scheme. So I'll be here now demonstrating or talking about some of the few studies or research we have carried out using ground-based LiDARs for creating a 3D documentation of the heritage structures. So the first study which I'll be just talking about is one of the site we took. We started initially with a church, which is the St. Mary's Church located in Lansdowne in Uttarakhand, the state of Uttarakhand. So you can see from here, the first aspect of creation of a 3D documentation using the lasers or model using lasers is the data acquisition. So data acquisition, how, and this, if you see, is a monument. How this what should be the appropriate locations for collection of data. So the entire monument was scanned using 10 to 11 scans from different positions, and these were taken, each scan will have a limited coverage. So for determining how many scans are required for proper planning, one requires to do a kind of a view shed analysis so that the entire structure can be covered in a minimum number of scans. So this is one way that if I keep my scanner in this position, which part of the monument would be visible, moving it another structure, which would be visible. So using this view shed analysis done, the optimum scans was identified, and from there, the data was collected, and this is the complete 3D model, which has been generated from 10 to 11 scans, which was positions from where that data was collected for creating a 3D model of the church. Then another experiment where we tried to integrate the active and the passive sensor. So as I said, LiDARs are the active devices and the passive sensor was the photographic pictures which were collected on ground. So both the instrumentations are on the ground, but to overcome or supplement the limitations of one another, the combination of these two technologies was done for basically 3D documentation, damage assessment, and reconstruction of the heritage sites. So in this case, we took up 3 UNESCO World Heritage Sites, which is Humayun's Tomb, Qutub Minar, and Nalanda Mahavihara. So Nalanda Mahavihara, as you know, is an ancient Buddhist monastery which has served as a lot of examples was also cited by Dr. Rajni, is a renowned center of learning in the ancient kingdom of Magda. So in case if we see, there are challenges also in the terrestrial laser data acquisition. So that's why we took a combination of laser scanning and photograph. So in this picture, if you see, when the object or the monument or the feature is the height of the object is very high, then again, you'll find there are missing areas where the laser scans cannot collect the images. There are shadows and occluded areas within the monuments itself. So in terms of where there are variations in point densities due to the shadows, occluded areas, monuments' height and horizontal expanse, the shape and complex patterns. So we need to do a combination. So a coupled here, the ground photograph using photogrammetric techniques. So using images acquired with an overlap of 80 to 90% were taken, and the point cloud generated from the photogrammetric process, point cloud generated from the terrestrial laser scanners were combined to create a seamless, with no gap, 3D model of these 3 heritage sites. So this was the entire methodology which was considered. We had a laser scan, as I said, terrestrial photographs, processing each independently. We created a 3D model, integrated together to then extract the extraction of architectural primitives, damage assessment, 3D, the digital blueprint, and subsequently we did an experiment for cultural reconstruction and visualization. We also collected the ancillary information. So this is actually the integration from data collected for the Qutub Minar from the different positions from a terrestrial laser scanners and the positions of the photographs. Using this, a complete 3D model of Qutub Minar. Similar experiments were done for Humayun's Tomb and the Nalanda Mahavihara. So from here, the point cloud could provide very accurately the height of the Qutub structure and even the monument, Humayun's Tomb, and even different monuments within the Nalanda Mahavihara. Then architectural elements, which are actually a unique detail and component parts that together form the architectural style of the monuments. To extract this point cloud data was very useful or very handy in helping in extracting the architectural elements. So these textured point clouds were using processing techniques, we're using filtering and egg extraction techniques were used to extract the architectural primitives. So you can see this is for the Humayun's Tomb, the different details of the different aspects. This is the window area where you can see each elements using filtering, edge extraction methods, and manual editing, the complete detail of each and every elements within the building was extracted. So this is another example of the architectural primitives which have been extracted for the monuments within the Qutub complex. So you can see very fine details were extracted, which can be used for later for later reconstruction or any kind of a damage assessment for each of the monument these structures. The structural health of a building are ascertained by, see, this is again the final blueprint from the Qutub point cloud, from the point cloud for the tomb of Imam Zamin in the Qutub complex. So this digital blueprint becomes a reference for future any kind of remedial measures which can be taken by the ASI or any agencies. This is again a 3D blueprint for the ground floor of the Humayun's tomb. So these are the top floor, so one can extract for the complete complex. Now, the structural health of a building are ascertained by identifying the damages such as cracks, which has developed due to over the ages due to vibrations or any natural phenomena such as earthquake, maybe due to the traffic, urban pressures. So it is essential to identify, it becomes, once if you are able to identify these cracks, and then one can take timely and appropriate interventions to repair and restore these important heritage structures. So terrestrial, in this case, again, since the density of the point cloud is so large and the precision is so high that the resolution, if I say, is very high, they can penetrate the fine crack depth. So, or one can automatically identify the cracks and the broken patterns in the built heritage by integrating the texture that is created from the photographic images and the depth information from the laser data sets. So the laser can penetrate the crack, and combining these two, one can easily detect the cracks in the buildings, and one can combine the two data sets to detect. See, if we do not use the depth information, then if you do directly segmentation techniques, many other features are also detected as cracks. But when we combine the depth information, which is provided by the laser, you can easily identify the other anomalies are removed. Then for for identification of broken patterns and damage detection, which are major in nature, besides the cracks, there are major damages in the built structures. Fractals were, we had utilized fractal dimensions for automatically identifying the areas where the damages are there, as fractals provide an insight in the local complexity in the geometry. So they give us the level of irregularity in the pattern. So fractals are replication of a pattern. So if wherever there is an irregularity in the pattern, these can be easily identified. So different techniques have been, we have utilized using various shapes and techniques of measurements to identify these areas where there are major damages. So once the damaged portion is classified, it can be replaced with a template at a suitable orientation for the virtual reconstruction. So here, if you can see, this pillar here is broken. So here, using the one on the left, the right one was reconstructed and then placed. So integration of this to create a virtual image of an area without the damage. So this is another example where, in this case, that there is a damaged part, and this is the actual one on the right-hand side of the pillar, where on the left side it is a damage. Using this was reconstructed. And another example is where the height of and the tilt of the Qutub Minar was also could be easily accurately estimated using this LiDAR point cloud. If we want to manually estimate the tilt in the height of the Qutub tower, it would have been tedious and time consuming. Whereas, it was said in 1964 when ASI reported that there is a southward tilt in the Qutub tower, and it is at an angle, with a shift in that direction of 63.5. When we measured with subsequently 2 years back, the shift was now observed around 64.29 centimeters. So there is not much variation from what was observed long back in 64. So the ASI had carried subsequent remedial measures to stabilize the area, so to prevent it from further tilting. So that has subsequently worked, and there is no significant tilt observed since 64. An attempt was also made to generate a conjectured models based on the clues obtained in the past, like what she said, Dr. Haratini, that she has used past photographs, past images, past data sets to understand the past landscapes and how to correlate with the current scenario. So here also we tried to generate a conjectured model, looked how this complex would have looked at the time of the construction due to the damages which occurred due to time. We tried to recreate the same information. So we try, here you can see this is the arch which is now broken. Using the information from the LiDAR point cloud and integrating it with the historical information, we could reconstruct and a simulation. It enabled us to create a simulation and the conjectural reconstruction of the past scenarios. So this is an example of a Qutb complex where the historical information was integrated with the laser scanners and the photographic data, and this was transformed mathematically and scaled geometrically to match each other, and it just enabled us to create a conjectural virtual reconstruction of the past scenarios. So similarly, this is for the arch. This, if you see in the past, photograph which was obtained for the Qutb complex, here there was a gallery or a boundary with a gallery here, which is only a part of is remaining. So we tried to reconstruct here for the entire gallery, and this is a textured model of the same area. So one can do a reconstruction. This is a conjectural reconstruction of monastery in Nalanda Mahavihar. So one can utilize this for and can be used to, for educational purposes, historical purposes, or virtual tour. One can utilize this information. And structures and artifacts, this is an example which we had done for Nalanda Mahavihar, where structures and artifacts which was obtained after excavation of historical significance are preserved in the museum there. So several such artifacts were unearthed and placed in the Nalanda Museum. And as again with reference to the photographic evidence of the exact location of the artifact which was available, it was possible to virtually relocate this 3D model of such artifacts at the accurate position, actual position, to create a photorealistic simulated view. So the simulated virtual model of Bodhisattva, Nagaraja, and the standing Buddha statues, along with, it's shown here. So we tried to put, these were the actual locations. Now this statue is placed in the museum. So how it would have been actually its location, it has been virtually placed. So a virtual scenario has been generated using this LiDAR. Could be possible because of the information generated here. So if you see, this is how this has been placed here. So using this data, a comprehensive documentation of both exterior and interior of any monument structure can be made. Even of the landscape areas can also be done to a certain limitation, and a photorealistic walkthrough can be generated. At the end of my talk, I'll just play that photorealistic walkthrough, what we could generate for this area. Another aspect is we had used primarily the terrestrial laser scanners and ground-based photographs, but one can also integrate this terrestrial laser observations along with the airborne information from the drones. So they will provide a huge, again, the issue with the terrestrial laser scanner is the rooftop canopy information is not there, and time consumption at certain locations. So we can complement it, supplement it with the drone-based data sets, and it can enable us or improve the representation of the entire 3D documentation. Another aspect is the integration of two active sensor data sets, that is laser and SAR remote sensing. So SAR can provide you surface as well as subsurface clues. They can also penetrate vegetation canopies and help in revealing buried on hidden sites. It can also penetrate the subsurface features. and reveal buried objects. So smaller, when we want to study smaller archaeological mounds that are critical to understanding human interventions, LiDAR is there. When we couple the two together, it can help us in better understanding the landscapes. And for the future researchers, one can use deep learning algorithms to automatically classify archaeological sites directly from a 3D LiDAR point datasets and improve the accuracy of identifying small archaeological features beneath the deep canopy in diverse environmental conditions. So this is the entire work which I had shown about our done at IRS is a contribution from a team where we have two scientists, Dr. Hina and Dr. Poonam, and there are 3 JRFs who have contributed in this entire project. And now I would like to play for you the photorealistic walkthrough which we created for the site. See, this is a complete walkthrough for the Qutub complex. And this consists of no photographs. These are just the point clouds which has been created using laser scanner coupled with the photographs, which also using photogrammetric techniques provides you point cloud information. So the 2 point cloud data has been put together to create this entire virtual tour of the Qutub complex. As you can see minute details, each and every inscriptions, complete complex area with a much as if you were present in the same location.
Thank you so much, ma'am, for such an interesting session. Ma'am, we have received a few questions. With your permission, can we take up those questions?
Yeah, sure.
Yeah, ma'am, the first question is, what are the challenges of bathymetric LiDAR in marine archaeological discovery? And our audience also want to know, is any project going on in India to map underwater archaeological sites using this technology?
Currently in India, I haven't heard of anybody using it, but there was a proposal to study on the Dwarka part of it. So that was long time back, but that never materialized as such, using not bathymetry LiDAR, but other underwater photographs. Because bathymetry LiDAR have a limitation. They cannot penetrate when there is a turbulence. They have a limitation of depth. So in a very shallow regions, this can work in the coastal areas. But deep down water, bathymetry LiDARs will not be able to give you much of information. So the prime study which was proposed was to use the remotely operated vehicles which can go down beneath water and collect photographs and process them using photogrammetric techniques to try to generate a 3D information from the subsurface features, but not with the LiDAR part of it. LiDARs is primarily with the areas in the coastal where in the shallow part of it, because they have an issue with the deeper surface. And if there is a turbulence also, there is a problem with the water. If there is clear water, then it gives you. If water is having sediment or other issues, then LiDARs will be a problem.
Okay, ma'am. Ma'am, even though you have explained it in your presentation, but one of the viewer has asked how the features below the surface can be identified. So can you repeat it once again for the benefit of our audience?
Below the surface means below the ground.
Yes, ma'am.
So for that, as I said, subsurface features, as I said, SARs can be used. Ground penetrating radar, we have ground penetrating radars, which basically works by transmitting a tiny pulse of high frequency radio waves into the ground, and then record precisely in nanoseconds the time which it takes for those signals to reflect off objects or contrasting layers in the soil and return to the antenna. So it's basically the longer it takes the signal to bounce back, the deeper the item or the feature is. So we have different frequencies, and these depths can be used to visualize what is there beneath the ground. So they have been, GPRs have been used extensively to uncover the secret tombs or buried historical sites in Europe. They have been used at many locations. And we have GPRs with variable frequencies with variable depth penetration capabilities.
Yes, ma'am. Ma'am, one audience also wants to ask how much distance can this laser beam take up? Means
again, there are various types of laser scanners. You have a close range and a far range laser scanners. So we have 300 meters to few kilometers, 1.5 to 2 kilometer laser scanners. Also, you get it. So based on the instrumentation you have a short range laser scanner. It has its own. So each laser scanner has its own characteristics or technical specifications. So you have a close range ones, which is often a range of 100 to 200 or 300 meters. Some have far range lasers, which provide you with kilometer to or more, around less than 3 kilometers or so.
Thank you so much, ma'am. Dr. Rajini, are you online? We have two questions for your particular session. If you are online, can you please unmute yourself?
Yes.
Yeah.
Yes,
Okay.
I am online.
Thank you so much for joining us online for the question answer. Dr. Rajni, one of our audience want to ask that in case of extreme weather events, so lot of damage would happen to our cultural heritage. So can remote sensing and GIS be used to detect these damages and maybe save, because they want to ask whether we can save our monuments or not. So what is your take on this?
Yeah, first of all, thank you very much for accommodating my live question answer session. I'm on the site, on a site visit. That's why I couldn't present live. Extreme, I mean, we obviously can't stop any extreme weather event, but we probably can assess locations for extreme climatic events, like sites that are on the coast, sites that are on the coast that are prone to tsunamis, sites are in locations that are prone to floods. For instance, there is a site along in Bihar, along where Koshi floods, for instance, regularly. So I feel what we can identify are sites that are prone to regular extreme weather events like floods and so on. Again, things like tsunami are much more rare, but we can identify those and try to see how best we can protect them. For instance, in Mahabalipuram itself, there were past paintings and records which showed Shore Temple to have been the waves coming and hitting the Shore Temple regularly. So they built a groin wall, which I think was a good thing, though many historians, art historians, had a very negative opinion about the groin wall because it really separated sea from the Shore Temple, and you don't anymore see the Shore Temple as Shore Temple. It puts it in a pedestal. But I think as a result of that construction of groin wall, it really didn't get affected by tsunami. So I think identifying monuments which are prone to disasters, and then protecting them is a possibility. And remote sensing can help in identifying the vulnerability of sites that are prone to such disasters.
Thank you so much, Dr. Rajni. And there's one more question. Our audience want to ask what type of remote sensing data should be required for archaeological investigation in the terms of spatial resolution, spectral resolution. So on this, if you can just brief our audience.
Sure. Actually, in my talk also, I tried to highlight how sites are different in 5 different ways. They are different because of the kind of, if you're studying a Buddhist site versus a Mughal site and so on, the kind of patterns you have to see is different. And they are different in their natural setting and subsequent natural changes, like whether they're in the plains, whether they're in the river banks or in the arid zones and so on, and subsequent natural weathering like floods and so on. And similarly in data availability and what is the historical work that is done. So all sites are fall into can be different in 5 different ways. So if you look at the permutation combination, it's very difficult to find any 2 sites that have exactly same of all these 5 things, 5 categories. So in that way, I would suggest, I can't say that this is the best resolution for every site, any site that you take up. And with remote sensing, it is unlike LIDAR, which just now Professor Dr. Shefali Agarwal explained, which gives the details of architecture and so on. With remote sensing, it is more location and the landscape that it can contribute to. So when you can see a plan of a structure probably, but what you can also see is how the local environment affects the site and how the site has affected the local environment. So you have to have an assessment of what big structures you are likely to see and what kind of structures. Are they water bodies? Are they fortification and so on? And based on that, one select what kind of spatial and what kind of spectral resolution one can look for. So I think the best way to do is to look for others. If you're working on a site, think of other sites on which remote sensing has been successfully applied and try and use similar resolutions and imagery. It is difficult to give a prescription of this is the best data or this is the best resolution for all sites.
Yeah, so it cannot be generalized. It has to be site specific.
Yeah, it has to be site specifically tuned what you can use and how you can apply.
Thank you so much, Dr. Rajni, for answering these questions and joining for the question and answer session. So with this, we come to an end of our
Thank you.
National Science Day celebration. So before ending the session, I would like to thank the people who were involved in all this celebration. First and foremost, I would like to thank President ISRS, Dr. Prakash Chauhan, and all the EC members for selecting this particular topic for National Science Day celebration. I thank President ISRS and EC members for all the support and support for this particular celebration. I thank all the 3 speakers, namely Dr. V.N. Prabhakar, Dr. M.B. Rajni, Mrs. Shefali Agrawal, for agreeing to deliver their talks in spite of their busy schedule and clearing the doubts of our audience. I thank Secretary ISRS, Dr. Praveen Thakur, for his support and keen interest in the entire celebration of National Remote Sensing Day. I thank the staff of ISRS for conduction of this program. Lastly, I thank all the audience who have sat all through these 3 sessions to make this celebration a grand one. Thank you, one and all. Dr. Praveen, would you like to say something?
Yeah, we can have one group photograph. All the speakers and members who are online in the teams, they can switch on their camera. ISRS staff, Dr. Philip, Dr. Behra, if you are online.
Good afternoon, Dr. Rajni.
Good afternoon. How are you, Dr. Shafali?
I'm fine. So where are you in field?
Amaravati. Behind me is the Amaravati Stupa.
Okay. So you're looking for something new there?
Yeah, actually, there was a fortification not far from here, so we came to look at the extents of that. And also, we had found some mound sort of symmetrically opposite to this, so going there too.
Yeah. Thank you. Thank you all for joining for today's Science Day celebrations. Hope we meet in person at Dehradun or some other common place this year.
Thank you. Thank you very much.
Thank you. Thank you.
Thank you.
And this recorded session will be available in our ISRS online lecture series for all those who are not able to join online today. Yeah, thank you.